Now, instead of the MH curve, if we look at the BH curve, that is magnetic induction versus magnetic field, that is also called a magnetization curve. So, alternative to MH, we can look at the BH curve, which is also called a magnetization curve. And the ratio, magnetic induction to magnetic field ratio, is defined as permeability. And we show permeability with the symbol mu. So permeability, which is defined as the ratio of magnetic induction to magnetic field H, is going to be in CGS EMU. Magnetic induction is measured in Gauss. Magnetic field is measured in Ørsted, so it's Gauss per Ørsted. Or in SI, since we have a magnetic field in Tesla, magnetic induction in Tesla, magnetic field is in ampere per meter. This is Tesla meter per ampere, which is also Henry per meter. So where does that come from? If you remember, we showed that flux, which is B times A, was equal to inductance times I. So we have Tesla meter square divided by ampere is Henry. So if you divide it by meter, Tesla meter per ampere is Henry per meter. So permeability is measured in Henry per meter or Gauss per Ørsted in CGS EMU units. Now, what does it do for us? Well, it's basically measuring how permeable the material is to the magnetic flux. So that's the physical meaning. It's a measure of how permeable the material is to the magnetic flux. And using our constitutive relations for linear materials, magnetic induction is magnetic field plus 4 pi m in CGS EMU. So this gives us, for the ratio B over H, which is mu, 1 plus 4 pi m over H, which is susceptibility chi. So it's going to be equal to 1 plus 4 pi chi. This is in CGS, electromagnetic units. On the other hand, B is equal to mu 0 H plus m in SI units. So B over H would be mu 0 times 1 plus m over H, which is mu 0 times 1 plus chi in SI units. So we see 1 plus 4 pi chi in CGS for the permeability, and it is mu 0 times 1 plus chi in SI. Now, if you look at the ratio mu r, which is mu divided by mu 0 in SI, this is 1 plus chi. That is also known as relative permeability. So with that, permeability mu is relative permeability times mu 0. Now, one thing I would like to note here is that what we call permeability is not the slope of the magnetization curve. So if you look at the magnetization curve, BH curve, for a ferro or ferri magnet, it's not linear. You see this initial magnetization curve. And if you look at a particular point P, and if you draw a line from the origin to that point P and take the ratio, the slope of this line gives you the permeability mu. Now, if you look at the slope at the beginning, you have initial value. So instead of mu 0, let's call this mu initial. And we see that in a typical behavior in the initial magnetization curve of a ferro or ferri magnet, the permeability increases and then it decreases. Now, if you look at the slope at a particular point on the curve, which is, for example, at this point at the beginning, mu I, the slope dB dH at that point gives us differential permeability. So B over H is permeability. However, if we look at dBdH at a particular point, it is differential permeability that we are looking at. So it's a matter of if you're looking at the local behavior or the global behavior. So if you're looking at the local behavior, you look at the slope of the line at that point. That would give you differential permeability. If you look at the slope of the line from the origin drawn to that point, that gives you the permeability. Now, as a second remark, I would like to say that if it's quite clear from here that mu is a function of H in ferromagnetic and ferrimagnetic materials. It depends on the magnetic field. And another remark I would like to make is that the value of mu is strongly structure sensitive. So if we, for example, look at the purity level of the material, heat treatment that is done to the material that may affect its crystal structure, any deformations of the material, etc., will have an impact on the value of the permeability of the material. So permeability reflects also structural changes that we might have in the material. So we can summarize the behavior of different types of magnetic materials. So as a summary, we can say if we start from empty space, for empty space we have no magnetization. So if we have no magnetization, that means chi, which is m over h, should be 0. So chi, which is dimensionless in SI, it is EMU per Ørsted centimeter cube. In CGS, EMU is 0. The permeability then becomes B over H, because m is 0, equal to mu 0 or 1. So mu is 1 in CGS EMU, mu is mu 0 in SI for this case. And there is no matter to magnetize. We have free space, magnetization is 0. The second type of material, diamagnets. So diamagnetic materials, we see that the susceptibility is small, it is negative, it is not temperature dependent. If we look at the corresponding value of mu, if mu is small and negative, then you can see that chi is small and negative will give us mu slightly less than 1 CGS. It will be slightly less than mu 0 in SI. And for the case of paramagnetic and antiferromagnetic materials, the value of susceptibility is again small. It is positive, greater than 0. It is temperature dependent. For paramagnets, chi varies as 1 over T. For antiferromagnets, we have chi increases with temperature and chi decreases with temperature after the nail temperature. So we have 1 over T behavior where it becomes a paramagnet again. We will talk about the exact temperature dependence for this later on. The corresponding value of mu is basically slightly greater than 1. If we're using CGS units, it's slightly greater than mu 0 if we're using SI units. So remember, we had this plot, chi versus T is like that. For the antiferromagnet, chi versus T is increasing first nail temperature and then it decreases as 1 over T. For the diamagnet, it is temperature independent and negative. Now for ferromagnetic or ferrimagnetic materials, ferro and ferrimagnetic type, we have chi and mu are large. They have large values. They can be 1000, 10,000, etc. So in this range, and they are positive. Chi and mu are positive, and they are functions of magnetic field. They depend on the magnetic field. Now on the microscopic scale, so if we look at microscopic scale, we see the following for magnetic moments. When we have a zero magnetic field, so I'm looking at this at zero magnetic field, in paramagnets we have a random distribution of magnetic moments. In antiferromagnets we have two sublattices. One type of moment is pointing up, so let's show it with blue, and one pointing down. Let's show it with red. So we have up moments and down moments, and you can see they exactly cancel each other. The total magnetization M is 0. The total magnetization for the paramagnet is 0 for a different reason, because we have random distribution of moments. In ferromagnets, the total magnetization at a zero magnetic field is non-zero. There is some magnetization, and we have all the moments pointing in the same direction on the microscopic scale, although we will see that it actually forms domains later on. But if you are looking at a small enough scale, you will see all moments pointing in the same direction. In ferrimagnetic ordering, also the magnetization is not zero. The difference is that we have, similar to the antiferromagnets, up moments and down moments, but down moments do not exactly cancel up moments. So we have a net moment which is pointing up in this case. So the total magnetization is not zero. So we have talked about permeability, which is the ratio of magnetic induction to magnetic field. In CGS EMU, it's measured in Gauss per Ørsted. In SI, it's in Henry per meter. And mu is a measure of how permeable the material is to the magnetic flux. Using our linear materials, linear relationship, B is equal to H plus 4 pi m, we see that magnetic permeability is 1 plus 4 pi susceptibility in CGS EMU, mu 0 times 1 plus chi in SI. And mu 0 ratio, mu r, is equal to 1 plus chi in SI. So mu 0 is 1 in CGS, so that doesn't give us a different value. If you look at the slope of B to H by drawing a line from the origin to the point of interest, we get permeability. If you look at the local slope at that point, for example, if I look at this point P prime and I draw a line here, so I look at the slope at this point P prime, this is going to give me a differential permeability. So at that point. And that is not the same thing as drawing a line from the origin to this point. This is going to be a different line and different slope, as you can see here. Now, the typical behavior of ferromagnets or ferrimagnets is that we have in the initial magnetization curve an increasing permeability at first, and then it starts decreasing. This is when we are magnetizing the ferromagnet or ferrimagnet starting from zero magnetization initially. We will talk about how to get zero magnetization in ferro or ferrimagnets later on. This value of mu is strongly structure sensitive. It depends on the purity of the material, the types of treatment that may affect the crystal structure and deformations, etc. So we can summarize our results as for empty space we have no matter to magnetize, capital M magnetization is 0. That means you will have chi equals to 0 and mu is equal to 1 plus 4 pi chi. Chi is 0, so mu is 1, or mu 0 1 plus chi, which is mu 0 in SI. So that's why mu 0 is called permeability of free space, because you have no material to magnetize. So let's note that here. That is permeability of free space. Now, for diamagnetic materials, chi is small negative. It is not temperature dependent. The corresponding value for mu 1 plus 4 pi something small negative will give us something less than 1. So you will be subtracting a small number from 1, or subtracting a small number from 1 also in SI, so that will end up giving you something less than mu 0. For paramagnets or antiferromagnets, chi is small and positive. It varies as 1 over T for paramagnets. For antiferromagnets, first it increases and then it varies as 1 over T after the nail temperature. The corresponding value of mu is small, greater than 1 in CGS, greater than mu 0 in SI. For ferro or ferrimagnets, chi and m have large values, 1000, 10,000, etc. They are positive and also field dependent, as we have seen in the initial magnetization curve of a ferromagnet or ferrimagnet. On the microscopic scale, if you have zero magnetic field, a paramagnet will give you zero magnetization with random orientation of moments. An antiferromagnet will give you zero magnetization with two types of moments pointing in opposite directions, compensating for each other. For a ferromagnet, after magnetizing the ferromagnet going back to zero field, we will see non-zero magnetization, all the moments pointing in the same direction. That is, strictly speaking, within a domain. So We're assuming that our scale is small enough here. For a ferromagnet, on the other hand, we will see moments, up moments and down moments that are not exactly compensating for each other, so that we have a net moment in a given direction.